Okay, we have 3 talks coming up about concurrency and linearizability. The first talk will be given by Abhishek, and this is going to be about reasoning about linearizability in the context of relaxed memory. Go ahead.
Yeah, thank you, Tej. So this talk is based on a joint work with my host Ori Lahav at Tel Aviv University. So let's begin the talk by assuming a simple scenario where a programmer wants to write concurrent code for his project development, and he is working under the relaxed memory programming model. So he wants to make most out of this relaxed memory setup, but he is also worried about the kind of problem or challenges that occur in relaxed memory concurrency, primarily due to difficulty in predicting the non-sequential behavior that his current relaxed memory model may allow. So in such circumstances, it is really helpful if he has access to if he has access to a specification, if he has access to the specification for a library which implements most routinely available data structure and functions in a highly efficient way. Now, in the present work, we assume a specification to be just another piece of code which may be more accessible for the programmer. Now, the primary contribution of our work is to identify library correctness condition for relaxed memory programming. We want to know what sort of conditions can ensure the soundness of client program that are developed solely based on the specification given by the library. Now, just to make context more clear, we are working with weak memory model of a C11 style memory model where we assume there is no read from future behavior. And yeah, so for the detail you can read our paper, but for the purpose of the talk it is sufficient to, if you understand the behavior of these 3 sample programs, where in the very first program, due to this release acquire read-write pair, you cannot observe a 0 at this place, while in all the other 2, since one of them is in relaxed access mode, you can easily observe this behavior here. So that should be enough for this talk. There are already some existing work on library abstraction under weak memory model, and these are some of them. But I mean, yeah, there are many other interesting work. So the important thing we want to emphasize here is that all of these approaches are based on partial order execution traces. So what we instead want in this work is something similar to the classical linearizability, which provides operational condition for library correctness based on totally ordered history. So when we say totally ordered history, we mean a sequence of call and return of library functions recording the local state of corresponding thread at the moments of the client library interactions. For instance, in this first work, I mean, this is first work which tries to do this for sequential consistent memory, and this was the work which addresses 886 TSO architecture in a same way, in an operational way. So what we want to do in this work is consider an even weaker memory model. So now going further, we also want to provide support for library calling policy in our in our work. So in a way which is actually proposed in this work by Khaija and Lahav, where the developer of the library can use a program called MGC to put meaningful restriction on the way in which the library can be used by a client. Okay, so for example, I mean, there are 2 sample MGC that we have given. One is MGC free, which almost puts no restriction on the client, but on the other hand, this another MGC can represent some restrictions by the developer. Now, what we are heading finally is towards something like this, an library abstraction theorem, where our end goal is this behavioral containment, and we want to identify these conditions. Now, using MGC, the library abstraction theorem can be visualized as a formal agreement between the developer and the client of the library, where this is the client's obligation which ensures that all the history of program using specification are in the scope of MGC. So they are covered by MGC, and the developer's obligation ensures that all the history of MGC using implementation can also be produced using the specification. Okay, so this is what developer has to. So, and we call it L refines, implementation refines the specification with respect to MGC. However, it turns out that in its present form, the theorem is not provable, as we are going to see with a running counter example in the next slide. For example, consider a library that implements function f and g in this way, where f essentially writes the value 1 to x and g reads the value from x, and the specification is yet another code which uses release accesses in these places. Okay, release and release acquire accesses. So the specification uses strongest release acquire mode, while this actual implementation has this relaxed accesses. Now it is, one can convince with some effort that this is true for this given, and I have not mentioned MGC. So MGC puts this restriction that f and g are called exactly once in different threads. So if you see, I mean, L actually defines L sub with respect to MGC. I mean, it can be seen easily, and for a given program like this, it is easy to see that this program is in the scope of MGC, right? Because it uses f and g exactly once in different threads. Now, since we could fulfill both of these obligations, clients and developers and clients obligation, so therefore we can hope to see behavioral containment as guaranteed by the theorem that we aim to prove. But this is not true, as we will see again in the next slide with example. So now see this program, when it uses the implementation, you can easily get this behavior here, because implementation uses this relaxed modes for this message passing is via this relaxed mode, and you can easily observe it. But the specification uses release acquire mode, and due to this release write pair, you have a synchronization, and this thread knows about of this write, so it cannot read from a previous write. Okay, so this is what happens when you work with the specification, and you cannot explain this program behavior. So the key observation here is that standard histories are unable to reflect the synchronization induced between calls and returns of library function when even if they are internal communication when this is release acquire pair. So our approach to solving this problem is based on what we observed in the previous slide. We come up with a novel operational semantics that necessarily exposes this crucial information about release acquire communication. And we also revisit the definition of history to correctly include this essential information recorded in the transition level. So now let's quickly understand the new operational semantic with a very simple example. In the new semantics, every thread has a knowledge set which it uses to record event known to it. For example, here, sorry, here these are the knowledge sets for the two threads, and whenever event takes place on any thread, it automatically gets added to its knowledge set. So for example, when this happens, this gets added here, and when this happens, again it adds this to the knowledge of thread 1. And when this release, this acquire it tries to happen here, it cannot happen because our new semantics now requires that the corresponding write be in the knowledge of this thread. Then only it allows this acquire it to happen. Now this write can be propagated to the second thread by an explicit propagation step in using our new semantics. But again, since this write is a release write, our semantic requires that all the earlier events be also propagated before this gets propagated to this one, and hence these things has to be propagated, and after this earlier event has been propagated, this write can get propagated, and hence this read can happen. So at the moment when this read happened, you can see this is already here in the knowledge of the second thread. And when you try to now execute this instruction, you cannot observe a behavior like this because thread 2 now knows of this write, which is a later write than the initial write, and you cannot observe a value 0 at this moment. So this is how roughly our semantic works. We skip a lot of detail in the interest of time. So, but I think this would be sufficient to explain the main idea of the paper. Now coming back to our running counter example, if we now try to use our new semantics and see what's the difference between the knowledge space of thread 2 in both the cases. Now it is easy to see that if you want to have this event here, all this has to be there, right? Due to the release acquire communication going on here. I mean, the semantics that we discuss right now will ensure that these things are present here. But in this case, you will not have this thing present here. Now, the question we want to ask at this moment is, can we observe this difference in knowledge set using some linear history? So this is what we want to ask. So we certainly have a difference in this knowledge set, but can we observe this difference using linear history? The answer is yes, we can do it if we enrich our notion of a standard history and also include now the propagation of call and return into history. So earlier, the standard history only contains call and return, but now we also want to include propagation of this call and return into the history. Now using this new definition now, it should be easy to see that while this is a valid history for this program, this is not a valid history for this program. And why is it so? Because you see, I mean, when this has taken place, you know that this has already taken place, and all of this should be present in thread 2's knowledge. But I mean, how can this appear here without getting explicitly propagated from thread 1? Because this is not an event from thread 2. So it has to be propagated by some explicit step. And if it is propagated using an explicit step, then it must be recorded here, because this is how we define our new notion of history. So, for example, I mean, this may be one position where it may occur. And therefore, we finally come to this conclusion that this is not a valid history according to our new definition of history, and hence the developer's proof obligations are not met, because this program was in the scope of MGC that we discussed initially, but it does not refine, I mean, this thing, right? So the L does not refine L surf anymore, and the same example that we saw as a counter example earlier is no more a counter example with this new definition of history. So now coming to our result, we saw that this new semantic that I just briefly described is actually equivalent to the RC11 declarative semantics. And following this, we proved that this library abstraction theorem actually holds with this new definition of history. Now, we also, I mean, our library abstraction theorem also provides data race freedom guarantee. So in C11, data races are undefined, behavior, and library abstraction theorem provides data race freedom guarantee. I mean, we can prove this, provided you fulfill some additional requirements. From client, we require that he should also confirm this thing, and from developer, if we can ensure that this is true, then in that case we show that this also holds. So this is part of our library abstraction theorem. In fact, in our paper we argue that the more generalized notion of data race freedom, which is called local data race freedom, can be derived as an instance of our library abstraction theorem. This local data race freedom guarantee ensures strong semantics for only those locations which are accessed by non-RESI accesses. Now, by appropriately choosing an MGC, which we call here MGC DRF, and a library, we saw in the paper that library abstraction theorem actually reduces to this. So, so you can get this as an instance of library abstraction theorem. So I will not go into the further detail, but I mean, for detail you can just refer to our paper. The important thing to note here is that in the local data race freedom guarantee, while trying to validate the precondition, you can assume strong semantics for those locations which you are talking about. And here also, to ensure this, we only need to think in terms of what's given in the specification. You don't need to get into the detail. So I mean, this nicely corresponds to the scenario situation here. And I mean, this naturally converges to the notion of this refinement. So while working on the release acquire model, we realized that release acquire accesses are sometimes too strong for a specification, and we introduced an intermediate access mode which we call partial release acquire. I will not go again into the detail, but with a simple picture, I can show you the difference. So what this partial release acquire does is that if, let's say, you have a partial release acquire pair like this inside the library, it will only impose, or I mean, it will only impose induce synchronization for the library and not for the client. So this is completely valid. I mean, this read can easily read from y if y is outside the library variables. But on the other hand, if your y is, let's say, a library variable, then this kind of communication can prohibit this kind of behavior where this read cannot read from this one. Okay, so this is this gives you a strong behavior for only for intra-library property, but not for the client part. So again, I mean, to for detail look into the paper, we have actually an implementation of concurrent queue, and we have given a specification using this partial release acquire, and we also show a refinement. We give a proof of refinement, proof of refinement with respect to an implementation which does not use any of this partial release acquire access, and which is based totally on weaker accesses. Now, as another application, as a final application of our work, we came up with a log-based specification for RCU primitive under weak memory model. Now, RCU is a synchronization mechanism heavily used in Linux kernel that allows a single writer to safely manipulate a data structure while multiple readers are concurrently accessing it. Okay, so unlike other existing axiomatic ad hoc specification, we believe our approach is more accessible since RCU calls in the client program can easily be understood by a standard log, because our specification is based on these standard logs, and we have used this FDR refinement checker to verify this for an implementation which was actually suggested in this, which we adapted using our release acquire semantics. And one thing to note here is that this refinement checking was possible because our correctness criteria was based on totally ordered history, and it was easy to encode these notions in this FDR refinement checker. So yeah, so just to summarize, I mean, these are our conclusion that we came up with a library abstraction theorem for CU11 style memory model, and our correctness conditions are actually operational, which uses totally ordered history. We came up with a novel operational semantics for doing all of this, and the result also supports for library calling policy, and we introduced a new access mode which we call partial release acquire access mode to the semantics of this language. Yeah, so thank you very much for your attention. I would love to have your questions.
All right, we have time for questions.
Zhong Shao from Yale University. Very interesting talk. So what kind of a relaxed library specification do you support? I can see you have a release acquire annotation over these operations. Is that all you have, or in the specification, what you can?
Okay, so I mean, for example, I mean, in this case, we came up with a concurrent queue data structure where we specify using partial release and partial acquire instead of release acquire. So I mean, are you talking specific to this one, or?
Yeah, I guess I'm just curious about what level of relaxed behavior you support. I can see. So implicitly, you are saying the in-queue has some acquire release annotation on it, and then you also have a partial release, partial acquire. Is that?
Right. So while specifying this, you can use partial release and partial acquire, but in the implementation, what we have is all relaxed accesses actually.
Okay, relaxed. Are these all the annotation you support, basically?
Yeah.
Okay, thank you.
My name is Jun Kang from KAIST, and thank you for a great talk. And I wonder how your particular composition story goes on. I mean, MGC is required for this refinement, and if you want to compose the two refinements, do your MGC conditions compose quite nicely?
So you are saying, I mean, if you use different MGC?
I mean, I don't impose, I'm not thinking about the specific MGCs. I'm just talking about composing two refinements under this MGC and how these MGCs compose.
I think the question is about transitivity of refinement, if you wanted to do this twice.
So I'm not sure about different MGC, but I mean, for the compose, let's say in the final thing also you should have some structure, right? I mean, you want, I'm not sure actually, I get the exact question.
So I thought I saw this in the paper. There's, you're able to combine two MGCs and link them together.
Yes, that's possible, right? So, so that's possible. I mean, we proved this compositionality result also in the paper, where you can, but there are requirements that you need to fulfill. I mean, so there are many sub-goals that you have to, prove for combination of MGC, and then you can probably get the final MGC. Yeah.
We had a question.
Hi, Jawang Jung from KAIST. So the motivation behind this partial release and acquire is seems to be that you want to hide the synchronization happens inside the library. So wouldn't it be easier to just prove a stronger specification for the library and then weaken the specification to a cleaner spec? So that's the approach we took in the Compass project. We prove a really strong specification, and then we make a cleaner specification suited for some specific use cases.
So, I mean, the strong guarantee that you're talking about actually can be derived from this partial release acquire also, where you take everything to be your set of concerned location. So what we say is that this will, having the partial release acquire will fill the gap between no synchronization and strict synchronization, which actually synchronizes everything. So instead, you can have now location-specific synchronizations. So this is how, this plays out in this one.
Thank you.
So, right. So.
We maybe have time for one more question. I can ask a question. Do you see any use for RC11P beyond what you did here? Do you think this is in general a better semantics? Does it have any other benefits?
I'm not sure about the semantics, but the correctness criteria is, of course, of interest because it's based on linear history, right? And if you have some tools which does this kind of refinement, can do this kind of refinement checker on linear history, then that you can utilize here. And this semantics gives us a way to get to that, linear history.
Got it. All right, let's thank Abhishek.